And we go and share the screen. And our chapter today is define what we mean by safety, since we are dealing with a class on safety analysis. And safety has a different meaning depending on the context in which we are using the word safety. And the meaning and terms that are used in safety analysis depend on the context and also the tradition of different disciplines in engineering and science. But as engineers and scientists, we need to quantify what do we mean by safety. And we have two bodies of knowledge to define what we mean by safety. One theoretically based on the theory of probability or probability theory. And in that case, the variables that we are looking at, like temperature, pressure, flow rate, are random variables. They're considered as random variables. So we'll dedicate a whole chapter in defining what we mean by random variables. But there is another theory that we have available to us. The name sounds the same as probability theory. People call it possibility theory. And that is also another body of knowledge where we can describe the same way as probability theory, the uncertainty that we have in events that occur around us. We'll see that in probability theory, we describe the uncertainty in measurements and observations, like we measure the temperature, for instance, we measure the flow rate, we measure any kind of variable that we are going to call later on a random variable. But when we deal with the meaning of linguistic variables, the meaning like hot, cold, tepid, high, low, safe, unsafe, all these linguistic variables are not describable by probability theory. They are described by what we call possibility theory. So this is another theory that we'd like to cover in terms of dealing with safety in general. When these variables depend on more or less like numerical simulation, modeling, or just maybe asking an expert, what is it that we mean by by a possibility, then we'll find that we have another theory. Now, an interesting aspect of this is related to somehow our own research here, is when you combine the two theories, probability theory and possibility theory, you come up with something that's even more solid and more useful when we deal with a coupled probability possibility theory, as we are going to learn together. So in that case, we deal with something like a random variable, like temperature, and then you say temperature is hot or temperature is cold. You see here we have a random variable, probability theory, temperature, a measurement, and then we give it a meaning, hot, cold. And in that case, you are not dealing just with data, but you are dealing with data that has associated with it a meaning. And when you associate meanings with data, it is not data alone, it's information. So as humans, in our world, the everyday's world, we deal with information. For instance, you are driving your car, you do not just look at the measurement of on the speedometer, but in your mind, you process the data and say, oh, the speed is too high, maybe because the roads are becoming icy or it's becoming dark. So you take an action and decision and reduce your speed. Say you, in the morning, you look out of your window, you find that it is raining. So in that case, you say that atmosphere is rainy. And you take a decision maybe of carrying an umbrella and so on. So there are three levels when we deal with data in life. We can get just the data, example, temperature, but then we move from data to data with a meaning, and that's what we call information. And it turns out that when we develop robots or computers, we are moving from just dealing with data alone into dealing with information, like that's sixth generation computing. And we are building the computers that deal with information rather than data alone. Example, the autonomous cars that Tesla is trying to do, right? It decides whether it applies the brakes or not apply the brake, getting close to the car in front of it or not. So in that case, this is a new revolution in computing. But from there, we can describe a higher level of dealing with knowledge around us, around the world, and that's knowledge. Knowledge so far is basically the realm of our intellect and humans. I don't see us having robots or artificial intelligence. Maybe it can deal with information for us, but knowledge is going to be left for us as humans. And some people even, warn us about allowing our machines, in that case robots, to deal with knowledge. In that case, it is not acceptable in general. Alvaro, I admitted you, but I don't know how to get you as a. I'll stop the sharing, then I'll go here. I think I'll allow you to make you a co-host in case we have two people taking it, I think, online. Anyway, so now I have to go back. All right, so we know now that we have to develop two different theories and then combine them together. The schools of science and engineering, you'll find that probability theory is the theory that's always adopted on the East Coast, like universities like MIT. You'll find that the possibility theory is more or less adopted in schools and universities on the West Coast, like Berkeley University. And I visited the MIT at some point, and they started arguing that, well, possibility theory is maybe probability theory when we take an infinite number of states in describing the system. So what we want to do today is describe how we define risk and for different contexts, and then later on over the whole rest of the semester we'll deal with the probability theory as being the state of the art today, but possibility theory as some kind of future way of dealing with uncertainty, and then the even more stronger and more powerful way when we deal with a coupling between probability theory and possibility theory. So let us see how risk is basically described in different contexts. The word accident is a description of an event that is undesired that can cause either damage or injury. And the damage could be, say, on property, but it could be also on health, somebody losing an arm or a leg. And in the medical, as I said, it depends on the context. In the medical profession, the term injury is preferred to saying accident. In the engineering field, we all know that when an undesired event happened, we call it an accident. In the medical profession, they suggest that an accident means an event, that it is an event that results in injury. So you could see here, it has to do with safety in general. If we consider accident, then whether it's in the medical community or the engineering community, you'll find that accidents can be an accident with a direct consequence. For instance, you get a chemical explosion, you get a big explosion, property is damaged, and hopefully some people are not hurt. It could be an accident resulting in an increased probability or possibility for injury or damage. And that could be an example, the cancer risk from exposure to chemicals or to radiation, say from a nuclear accident, or to chemical injury. We mentioned the Bhopal accident in India, where an insecticide plant exploded and spread the insecticides into the lung of the surrounding community, and they're still suffering out of this until today. There are accidents that can result in the degeneration or the continuous occupational exposure to gases, chemicals, or noxious substances. We can take as an example, in that case, coal miners. What is the affliction of coal miners that you have read about? When coal miners go into the mines, what do they get as a continuous, yes? Yeah, this is what's called black lung disease, basically the inhalation of the dust from coal into their lungs eventually makes them very, very, very sick. People who mine uranium underground, not above ground, but underground mines, oh, they get the radon gas also in their lungs. That's why, as engineers, we have to ventilate those uranium mines very, very powerfully. Farmers get, and construction workers get dust in their lungs, and that is named, in that case, a disease that's called silicosis, because they get silicon dioxide, which is sand, also in their lungs. So in that case, the occupational exposure can lead to what we call morbidity. They become sick. It's not death, but morbidity. And we talk also about accidents resulting from sabotage events caused by willful action. This includes acts of terrorism against civilians and non-combatant individuals or group of individuals. All right, so this is the terminology. Accident, injury, and different forms of accidents can be considered. Sometimes the terminology uses the word incident. So what is an incident? The definition is an undesired event. Oh, that can cause either damage or injury. And the damage, as I suggested, could be to property, but it could be also monetary. You can define the damage as being a loss of money in general. Some people use the term near accident that is used often to describe what we call an incident. In the nuclear and chemical industries, the word transient is used. This is also used to describe an incident. So what is a transient? Maybe by mistake, somebody fiddling with a screwdriver in a nuclear power plant, and then he increases the flow rate of cold water into the reactor. The cold water causes better moderation of the neutrons, and the power goes up. It goes up temporarily. It goes up and comes down. So people call, in that case, a transient. So that word transient is used to describe an incident. Hazard is the terminology for a probable, and I use the word probable because we'll use probability theory, or possible because we'll use possibility theory, cause of an accident. So an accident is caused by an existing hazard in general. The hazard could be an object or a situation. For instance, a car hitting a rock, the rock would be the hazard on the road from fallen rocks on a highway, but it could be also a situation, an icy road, that would be a hazard. This loss could be, in all these cases, caused by hazard. It could be economical, it could be monetary, a loss of money to repair the car, maybe injuries, disease, morbidity. Morbidity is not death. Death is when a person loses their life. Morbidity is when they become very, very sick and they cease to be able to be functional normally in society in general. And that leads us eventually to the concept of risk. And whenever we develop any kind of an economical or engineering system, we always like to define the risk. So in investments on Wall Street, they talk about the risk of a certain investment. But when we build a nuclear power plant or a wind turbine, we also speak of the risk of that it can entail to society at large. So risk is, again, the probability or possibility of an undesired consequence. So often it is considered a function of probability and consequence. We'll define the risk, in fact, as the product of a probability of occurrence multiplied by the consequence of the occurrence. Now, remember, in math, any of your math classes, when you dealt with probability, strictly speaking, in mathematics, probability has no units. So if we say that the risk is the product of the probability of occurrence of an event multiplied by the consequence, because probability has no units, you'll find that the risk takes the units of the consequence. And we'll see how this is developed later on. So risk sometimes refers to the likelihood per unit time of injury, illness, or death to people. But in that case, the consequence really is the injury per year or per day or per month, illness, people getting black lung, for instance, disease, or unfortunately to death. As engineers and professionals, death is something that we worry the most about, since the preservation of human life is very precious to us. It is also used when the outcomes are uncertain or not well-founded. And some definitions of what we'd like to call objective risk. And objective risk is a risk in which we are able to associate a number or compare it to another level of risk that is acceptable to us in society. If it is not an objective risk, it is a subjective risk. So in that case, we cannot measure it because it simply depends on the individuals and how they conceive of the risk. For instance, for me, riding a motorcycle is a very, I perceive it as a very risky event, but for some people, it's a fun thing to do. So the perspective of risk is not the same as what we try to do as engineers. We try to calculate what is an objective risk and give it a number. So in that case, it's a statistical issue. And risk in that case could be the probability of a loss, the size of the possible loss. It could be a function consisting of the product of probability and the size of the loss. This is the most common definition of risk. So let us define a very simple way for risk. We'll expand on this later on. So let's call risk here as a probability of the occurrence multiplied into the consequence of the occurrence. And we are going to put it in the form of a symbol here, probability multiplied into C, the consequence, because probability, again, I repeat it, has no units. So risk will take the units of the consequence, dollar lost per year, or injuries, loss of limb or car accidents per year, and so on. So this is going to be the most common definition of risk that we are going to use. It could be the variance of the probability distribution of all possible consequences of a risky course of action. So in that case, instead of taking a number like P, it can take a normal distribution or a log normal distribution or a Poisson distribution. It could be also a weighted linear combination of the variance and the expected value of the distribution of all possible consequences. And this is, again, what we are going to refer to as objective risk, a risk that is measurable, that we can quantify, we can compare to other levels of risk. Perceived risk, as I suggested earlier, is, from the psychological perspective, a risk judgment. That is an intuitive value judgment. It expresses a diffuse negative evaluation of a decision alternative. It could be a general feeling that a certain situation is undesirable. For instance, for me, bungee cord jumping is very risky, but for somebody else, it may not be considered as risky, and that's great fun. Jumping out of airplanes, parachuting, for me, it's a very risky event, but for some other people, oh, that's a pastime and that's something desirable that they pursue in their lifetime in general. So there is objective risk, we have to remember that, and a perceived risk that are really two different animals or objects in that case. So in that case, we come back to the concept of safety, since the whole title of what we are trying to learn together is safety. Safety then becomes not the opposite of risk, as some people would think as a triviality, but it's inverse. So in that case, if we want to think mathematically, we can say that safety is inversely proportional to risk. All right, so this is a proportionality constant. And if we say that safety is inversely proportional to risk, we can eliminate the proportionality sign, like in mathematics in general, replace it by an equal sign, provided we add a constant here in the numerator. So in that case, safety is equal to a constant divided into the risk. And that expresses the interesting mathematical relation here that the product of safety into risk is usually a constant. What does it mean? If you take a constant and safety is high, since it's multiplied into the risk, you'll find that if the safety is high, the risk is low, and vice versa. If the risk is high, you'll find that the safety is low, because both of them multiplied into each other should be equal to a constant. So that expresses the notion that if you have a high level of risk, you get a low level of safety, and the low risk value implies high safety. So mathematically, safety and risk are not two opposites. They are complementary to each other. They live together, so to say. When one is high, the other is low, and their product is always equal to a constant. Now let us talk about the property of risk. When we talk about risk, it is always associated with uncertainty. You cannot say that the risk is exactly number 2 or 1 or 0.1 or 0.2. It is always associated with uncertainty. So when we measure risk, we will always measure it and associate it with uncertainty. And if you remember your math or your statistics, or in fact some lab courses, uncertainty is usually associated with how the values that we measure are spread from each other. So in that case, we get a distribution function or a probability density function. Now, something interesting also difference between risk and uncertainty is that risk, as we'll see later, has a price in the sense that we can spend money to reduce the risk. And we'll come back to this as an example. And in other words, you can establish the probability of a loss and then give it a price in terms of spending money. For instance, an example of reducing the risk is life insurance. All of us here get some form of life insurance. In fact, by law, if you drive a car, you must have an insurance on the car, or you will be in violation of the law. When you graduate, and the first thing when you accept a job is an insurance agent coming to your office and trying to sell you insurance. And definitely for young people establishing families, there is always the risk of death. So in that case, they insure their family towards any calamity that can happen to the breadwinner in the family. So in that case, you'll find that life insurance is a pricing mechanism for risk. And you'll see that we'll cover that in more detail as examples. For instance, let's take a car, and to reduce the risk of death in an accident, car accident. By the way, car accidents are the leading cause of accidents in the United States. I think I showed that in a table in the first chapter. And to reduce the risk of death in car accidents, we start by having, let's say, seat belts. How much does a seat belt cost in a car? Can you tell us? Just give a number, any number. Seat belt. Pardon? No, we're not 10 times. But if you If you have an old car, an antique car, and you want to make it safer, you add to it a seat belt. You spend how much? Let's say $200, huh? $200, all right? Now, if you want to increase the level of safety, in that case, you reduce the risk. You go and buy a car, in that case, with anti-lock brakes, right? And anti-lock brakes cost you more than the $200 of a seat belt. So you spend $800. So you could see here, you have reduced the risk by spending a certain amount of money. Oh, you want to increase the level of safety of your car? Oh, get airbags for the driver, right? You pay another $2,000 in your car. You want to have even a higher level of safety, get not just driver airbags, but side airbags. Here you move into the BMW and the Mercedes and the Lamborghini. So you buy a reduction of risk by money. However, this is done up to a limit. We'll see later that you cannot reduce the risk ever totally to zero, but you can reduce it. And this is called the law of diminishing returns, in the sense that the more money you spend, the amount of reduction of risk decreases and decreases and decreases up to a certain point, because we cannot spend an infinite amount of money reducing the risks to zero. And professionally, as engineers and scientists, we know and we tell the public that risk cannot be made into zero whatsoever. All right, so we have to always accept a certain level of risk in society. The important aspect is that risk, well, example, life insurance, has a monetary value, and we can decrease it by spending money. However, uncertainty now cannot be priced. We don't have control on the uncertainty, the probability of, say, people getting into accidents, say on icy roads. This is there is an uncertainty level here. We cannot control that, but we can control the level of risk. So we have a when we design engineering objects, that's all we can do: reduce the level of risk by adding what we call engineered safety, ESF, engineered safety devices in general. So uncertainty must be incorporated in its different forms in the modeling and the calculation of risk. And see here I'm saying the word calculation of risk. We are going to calculate risk in engineering systems in general. There is a different concept associated with risk, which comes from the banking business. When bankers sell or buy bonds, I told you that risk is not just in the engineering field, but it's also in the monetary or the economic field. They come with the concept of security and the concept of surety. Surety becomes very important in application where you cannot allow events that are undesirable to happen because the cost can be extremely high. So you want to be sure, almost sure, that those events are not going to occur, and you spend all the money that you can spend to reduce it. Let's take as an example the storage of nuclear weapons. In that case, it is not enough to say, oh, the probability of a failure is so much and accept it. In that case, you want to be sure that your nuclear weapons are not going to explode all by themselves. So in that case, the concept of security and surety are composite information quanta. So quanta here is a plural of a quantum, of a little piece, like quantum mechanics deals with small pieces of particles. And this describes the degree by which a desired safety or a risk level is achieved. For instance, we can talk about security as the detection rate of radiation. Maybe you're measuring radiation is high. Surety would be similar. You can say the failure rate of my rocket or an airplane, engine on an airplane is tolerable. Notice here now in that case that we did not, as I suggested earlier, we did not use just a random variable X, which we can measure the failure rate by running any device and take, for instance, the door of a car, the failure rate. You open it and close it and close it and open it and close it 10,000 times by a robot, and then you measure the failure rate. So this is a random variable that in general we can give the symbol x2. But then when you say high and tolerable, there is, to your best knowledge, I think, any field of mathematics that describe something that's high or something that's tolerable or low, you'll find that this is not, this is a random variable, detection rate, a measurable quantity. But when you say high, this is basically a qualification of the detection rate being high. And notice here now that it's not just a piece of data. It's a data with a meaning. Temperature is high, detection rate is high, and temperature is low again. You have given a qualification to a measurement. In that case, symbolically, we can say that the random variable could be x, the measurable quantity, and we are giving it a meaning y, and we are going to call this a fuzzy variable. So high and tolerable basically can be described mathematically with the algebra of logic. So is the random variable here, failure rate and detection rate, but the body of mathematics describing the detection rate, which is a random variable, depends on what we are going to call in chapters to come. We call this the Boolean algebra. The name Boolean is a British mathematician that helped us define through the algebra of logic how to describe random variables. High is a fuzzy variable. It's a different body of mathematics, axiomatically described, but by another mathematical construction that we call a De Morgan algebra. So we have a Boolean algebra to be described later for the random variable x, and then we have high and tolerable, all those linguistic variables, another body of mathematics that we are going to call the De Morgan algebra, and this is another mathematical entity. When we talk about surety or security, you see here that we are not just dealing with a random variable, a measurement, temperature or pressure or detection rate. We are also giving it a meaning. When you give meaning to a piece of data, by definition, you could see that symbol here, equal with a little triangle on top of it. In mathematics, that means it's a definition. We call this a quantum of information. And this is where now we have progressed or evolved from dealing just with data, as we do in everyday's life, and in the engineering field, we deal with information. So surety and security are quanta of information. So you could see here that moves us in the engineering and in fact in the mathematics field one step higher in describing the world around us. Now, how can we quantify this? I'll give you today an example, but later on we are going to develop the theory in more detail and improve on it. In the definition of that information granule that we wrote up there, x is a random variable and y is the qualification as a linguistic variable. You can quantify, the random variable is based on observations and measurements, obviously. Probability theory applies. Y is based when you say that it's pretty, ugly. This is some kind of a subjective value. It can be based on a simulation, modeling, or in fact, an expert opinion. Tell him, oh, okay, do you think this is safe or not safe? And the random variable follows the laws of probability theory, but the fuzzy variable, the qualification, follows the laws of what we are going to call possibility theory. So there is probability theory, and there is possibility theory, and there are two different animals. Now, suppose that now we want to measure the level of how real or how is it that X is Y. temperature, how can we measure the granule of information or an information granule, that temperature is high or temperature is low. In that case, we convolute the probability distribution for the random variable, we'll call it P of X, and into the description of the fuzzy variable, the meaning, and we are going to give that a name. We are going to call that mu. That's a function of the variable that we are measuring. We are going to call this the membership function. And we'll describe what are the differences between a probability density function and membership function. When you combine the probability into the membership function, meaning you say, okay, the temperature is acceptable, the temperature is dangerous, maybe it can cause melting of fuel in a nuclear reactor. In that case, it's an integral over all the values of the variable that we are considering. But in fact, we can approximate this integral here by a summation. And the degree by which our observations, well, probability theory is observations, to the level that we would like to see as a membership function, this is called a convolution integral, and the convolution integral can be approximated by the product at each point of the membership function into the probability of the occurrence of the event. So and we call this quantity here the performance level, PL. And an example will show you what we mean by that. It becomes a very important quantity when we combine probabilities which are measurements to the level at which we want our system to operate. So if you are really monitoring a system in engineering, the relevant quantity is not the data itself, but the level that those data satisfy your needs in maintaining a certain level for each one of those variables, be it a level of water in a core of a reactor or the speed of a car on an icy road, any variable that you can think of, and an example will show us how that is going to be done. So let us take the temperature in this room, and we want to build a control system that would make the temperature tolerable in the room, or the temperature of the fuel in a nuclear power plant, or the temperature of the coolant in a car, whatever. So in that case, we define the variable that we call tolerable, which is the qualification that we are going to give to the temperature. And in that case, I would like my temperature to vary between 65 degrees to 80 degrees. Actually, I want it to be in between 65 and 75 and never exceed 75. So in that case, I describe the temperature 65 here, the level of temperature. And when I say 1, I want it to be at the level at 1. I want it to be at the level of 70. I want it to be at the level of 75, but not go to the level of 80 degrees. Obviously here, if we get in this room 80 degrees, it will not be tolerable. So let us show that membership function on a graph here, and we are going to use a discrete distribution of the variable. So let's see the numbers that I put in the example. 65, so this is the temperature, degrees Celsius, 75, 80, no, I took 70, right? I took actually 65. So follow the example on the screen, 65, 70, 75, and then 80. All right. So how do I show this on a discrete distribution? I go up here and take a little point and say that, oh, this is 1. And then I go here and show a little point here and say this is also 1. 75 is 1. Oh, but when we get to 80, it is a 0. Notice that this is not a probability distribution. Why is this? Because you have learned in your other classes that a probability distribution adds up to 1, and that will come later on. So this is what I would like to see in the temperature range. 65, 70 is okay, 75. So I give it a value of 1 here. So you could see here that what we have built here is what we call a membership function, and I'm going to call this mu sub x. We discovered that the membership function that comes to us from possibility theory can have values at 1 or below 1, but not less than 0. So I write here that mu of x should be larger than 0 and less or equal to 1. All right, now how do we use that goal that I want in my control system for this room, an air conditioner, for instance? Now I go and look at different temperature states. So let us take now the random variable, the measurement. The measurement that I go and take maybe at some point gives me a temperature distribution that looks like this. The one that I chose is 65, 70, 75, and 80. It showed up here at 75 here, 80% of the time. So that in that case, the probability here is 0.8. And then at 70 degrees, it is only 0.1. Follow the graph there on the screen. And then when I go and measure the temperature at 80, it is 10% of the time, that's 0.1. Notice here that I have now a probability P1, a probability P2, a probability here P3. And when you add P1, P sub 1 plus P sub 2 plus P sub 3, how much do you get? 0.1 plus 0.1 plus 0.8. Oh, you know how to add this. What do you get here? 0.1 plus 0.8 plus 0.1. How much is that? 1.0. So this is the definition of a probability distribution in general, is that the probabilities should be less or equal to 1 and larger or equal to 0. All right? So this is the temperature that I read here right now, maybe on a thermometer. And then that is just data. How do we turn it into information? By calculating what we defined as the performance level. I take the value of the temperature here at the probability at 70 degrees here, that's 0.1, and multiply it by the membership function that I want here at 1, plus the value of the temperature at 75 degrees in the probability distribution, that is 0.8. And then the value here, oh, it's 0.1 by 0, that's plus is 0, and it gives us 0.9. So in that case, if the measurement of the temperature varies between 70 and 80, my performance level, oh, we quantified how is it that temperature is adequate as we want it to be according to the membership function, and the performance level is 0.9. So I know that the performance level is 90%. So it is not 100% right, but it is 90%. If that is happening for me, where I am controlling any device, or if I am monitoring a device, oh, that is a very good level of performance. So what do? I do nothing. I let the system operate with that level of performance. However, if this is the temperature range that we want to be according to that membership function, 65, 70, 75, and then I go and measure the temperature and I get these values, 0.4 for the probability density function at 75 degrees and 0.6 at 80 degrees. So 40% of the time, the temperature is 75 and 60% of the time it is 80 degrees. And I carry on the convolution integral there. You find that you have here 0 multiplied by 1. Then you have another 0 multiplied by 1. You have that 0.4 multiplied by 1. And you have the 0 multiplied by that 0.6. And when you add that integral, well, we have approximated the integral by summation, you get only 0.4 as a performance level. So the matching between what I am observing here and what I need to see is only 40%. So we got there a level of what we call the performance level. If you are operating a car or running a factory, in that case, whatever device you are using is performing at the level of performance of 40%. So whereas in the previous case, it was operating at the performance level of 90%. So you could see how important it is in monitoring and control. At 90% level, well, we continue operation, but at 40% performance, something is wrong. So we send somebody to check the machinery that you have in that case. So you could see that when we combine probability theory, this is a probability theory, the actual observations that we get to the membership function, what we want to get. This is probability theory, this is possibility theory. You combine them together and you get something that's even more powerful than either one of them alone. All right, I'll ask you to work on the similar problem in the exercise that will be given to you today. You could see here that now we take another fuzzy variable tolerable, and we take again the failure rate is tolerable. So what is the level of surety? That would be important, say, if you are dealing with the engine of an airplane. You don't want that failure rate to be too high. I give you here a different levels, 0.1, 0.8, 0.1. This is a probability density that describes some measurements. I give you another probability density function, another set of measurements. You notice that the probabilities 0.2 plus 0.6 plus 0.2 add up to 1. And another level, 0.3, 0.4, 0.3. Take each one of them and convolute it with the membership function and calculate the level of performance in that case. If the level of performance is low, then sometimes we need to stop operation. If it is halfway, then that means that we stop, say, a production line and see what is wrong with it. And when the performance level is high, that's wonderful, we continue operation. And I'll give you an example for in real life. If you don't own a car, you'll own a car someday. And when the winter comes, we notice that the tire pressure in cars in general starts going down, right? And we are faced in that case with a decision, all right? If the flattening of the car is too large, then we have to stop operating the car. Maybe I have a nail in the tire and I have to stop operation when the performance level is very low. But sometimes we can run our car with, say, the tire slightly deflated. It can still operate. And of course, if it is very highly inflated, we run the risk of explosion. So we go and deflate the car. And so you could see here that we have a situation where we combine the, let me see here, that shouldn't be here. And here we need to maximize this. I don't know how. Oops. So the combination of the probability theory to possibility theory allows to do things that we are not able to do in our engineering devices today. Again, safety and security are associated with each other, and using the concept of a performance level can lead us to not just safety, but surety in identifying when accidents are going to occur. In fact, we can do it in an anticipatory way, in the sense that we don't wait until the accidents occur and become reactive, deal with the accident, but we can start predicting when the situation in a given device is headed into an undesirable level. And in that case, we can develop what we call anticipatory system or predictive systems for running engineering systems in general. And I'll stop the share here, and I hope that it recorded it, and working with the little assignment will help you understand why it is important for us to deal not just with probability theory,